15 billion miles from Earth, a spacecraft launched before the first personal computer existed is picking up a sound, a hum, constant, coming from a place every textbook said was silent. We thought we knew what was out there. We were wrong. 8 times. The boundary was 1.3 billion miles closer than predicted. The temperature was nearly double what physics allowed. The protective bubble around our star has no tail, no clear shape, and a wall that leaks. A 43-year-old backup transmitter fired up on its own from interstellar space. And a broken instrument that NASA almost left off the spacecraft ended up confirming the biggest crossing in exploration history. Over the next 2 hours, we are going to follow Voyager to the edge and beyond. If you enjoy the journey, hit like and subscribe. Now, let us begin, because right now, roughly 165 astronomical units from Earth, Voyager 1 is still listening. Its plasma wave subsystem has been recording a persistent narrowband emission since 2017, a steady tone in interstellar space, about 0.04 kHz wide, coming from a region that every model described as silent and empty. The probe left Earth on September 5, 1977. It was built to photograph Jupiter and Saturn. Nobody designed it to survive 48 years. Nobody imagined it would still be transmitting data from beyond the solar system's outer boundary, a region called the heliopause. But it is. And the data it sends back takes about 22.5 hours to reach the Deep Space Network's antennas, another 22.5 hours for any response to travel back. A 45-hour round-trip conversation with an object 15 billion miles away. The hum is real. It represents plasma vibrations in the interstellar medium, the thin gas that fills the space between stars. Think of it like the low rumble you hear when you press your ear against a seashell, except the shell is the galaxy, and the sound is electrons oscillating at frequencies Voyager's 1.6-watt instrument can barely detect. What makes this strange is not the hum itself. It is what the hum tells us about the space outside our solar system. The interstellar medium was supposed to be cold, quiet, and featureless. For decades, models described it as a vast expanse of nearly nothing. Sparse hydrogen atoms drifting in darkness, the kind of place where measurements would flatline. Instead, Voyager found structure, density variations, pressure waves, turbulence following patterns that physicists recognize from fluid dynamics on Earth, called a Kolmogorov spectrum. The space between stars has weather, and the hum is only one piece of what went wrong with our predictions. Every major boundary Voyager crossed was in the wrong place. Every measurement at those boundaries contradicted the models. The magnetic field was supposed to change direction dramatically at the edge. It barely moved. Particles that were supposed to peak at one boundary kept rising past it. The temperature outside was nearly double what anyone expected. 2 spacecraft crossed the same border 6 years apart and described fundamentally different things. 8 separate predictions about the edge of our solar system turned out to be wrong, not slightly off. Wrong in ways that forced entire fields of heliophysics to start over. The investigation that follows is into why our best models of the space we live in failed so completely, and what the real data tells us about the bubble of charged particles that surrounds our star and separates us from the rest of the galaxy. That bubble is called the heliosphere. We thought we understood it. We did not, and the evidence is still coming in, carried by a probe that is losing 4 watts of power every year, shutting down instruments one by one, transmitting on hardware built before the first personal computer existed. The interstellar hum continues. Voyager is still listening, but to understand what it found, we need to go back to what we thought was out there before any spacecraft had ever reached the edge. Before Voyager reached the outer solar system, the heliosphere had a clean, well-understood shape in every textbook. Our star sends out a constant stream of charged particles called the solar wind. This wind blows outward in every direction at speeds between 300 and 500 miles per second. At some point, the wind slows down. It hits the gas and dust drifting through interstellar space, and the pressure equalizes. That point was called the termination shock. Beyond the termination shock, the solar wind was supposed to slow further and pile up in a region called the heliosheath. Think of it like water from a garden hose hitting a wall. The water spreads sideways after impact, forming a layer of turbulence before dripping off the edges. The heliosheath was that spreading layer, and beyond it lay the heliopause, the final boundary where solar material ends and interstellar material begins. The heliopause was predicted to sit at roughly 150 astronomical units from our star. 1 astronomical unit is the distance from Earth to our star, about 93 million miles. So 150 astronomical units is roughly 14 billion miles. The termination shock was predicted at about 108 astronomical units, or roughly 10 billion miles. Beyond the heliopause, interstellar space was modeled as cold, sparse gas at temperatures between 15,000 and 30,000 degrees Kelvin. That sounds hot, but the gas is so thin that the actual thermal energy is negligible. A few atoms per cubic inch, barely interacting. Models predicted this gas would be featureless and quiet. The shape of the heliosphere was settled science for 50 years. Because our star moves through interstellar space at roughly 52,000 miles per hour, the heliosphere was supposed to look like a comet. A blunt nose on the leading edge, compressed by interstellar wind, and a long tail stretching hundreds of astronomical units behind. Every illustration in every astronomy textbook showed this shape. Every model calculated it. Researchers built careers on the comet-tail heliosphere. The magnetic field was another settled question. Our star's magnetic field spirals outward with the solar wind, forming what physicists call the Parker spiral, named after Eugene Parker, who first described it in 1958. At the heliopause, this spiraling solar magnetic field was supposed to collide with the interstellar magnetic field coming from outside. The collision would produce a dramatic change in field direction. A compass needle, if you could float one at the heliopause, would swing hard. That directional flip was the predicted smoking gun for identifying the boundary. Anomalous cosmic rays added another prediction. These are particles that start as neutral atoms drifting into the heliosphere from interstellar space, get ionized by solar radiation, and then get accelerated to enormous energies. The acceleration mechanism was supposed to operate at the termination shock. When a spacecraft crossed the shock, anomalous cosmic ray intensity should peak. Entire research programs were built around measuring that peak. This was the model. Termination shock at 108 astronomical units. Heliopause at 150. A clean magnetic flip at the boundary. A cosmic ray peak at the shock. A long tail. Cold silence beyond. 50 years of theoretical work, all internally consistent, all mathematically sound. The first crack came on December 16, 2004, when Voyager 1 had been flying for 27 years and was farther from Earth than any object humans had ever built. On December 16, 2004, Voyager 1's instruments registered a sudden change. The solar wind speed dropped. The magnetic field intensity jumped. Particle count shifted. The spacecraft had crossed the termination shock, the boundary where the solar wind slows from supersonic to subsonic speed. This was the moment heliophysicists had waited decades for. The location was 94.01 astronomical units. The prediction was 108. Voyager hit the boundary 1.3 billion miles closer to our star than every model said it should be. To put that distance in physical terms, the error in the prediction was larger than the distance between our star and Saturn. The entire model of where the solar wind first encounters resistance from interstellar space was off by a gap wider than the outer planets. The location was a problem, but what happened at the boundary was worse. Anomalous cosmic rays were supposed to peak at the termination shock. This was one of the firmest predictions in heliophysics. These particles, neutral atoms that had been ionized and accelerated, were believed to gain their enormous energies through a process called diffusive shock acceleration, bouncing back and forth across the shock front like a ball gaining speed between two closing walls. When Voyager crossed the shock, the intensity of anomalous cosmic rays should have spiked. It did not spike. The intensity kept rising. It continued increasing as Voyager moved deeper into the heliosheath, past the shock and toward the heliopause. The termination shock was not the acceleration source, or at least, not at this location. Decades of theoretical work on anomalous cosmic ray acceleration collapsed with a single dataset. Stamatios Krimigis, the principal investigator for Voyager's low-energy charged particles experiment, had built instruments that flew to all 8 planets. His detector was the one recording the cosmic ray data as Voyager crossed. The particles his instrument measured were real. Their energies were real. But they were not doing what every model demanded they should do at this boundary. The immediate question was where the acceleration was actually happening. Some researchers proposed that anomalous cosmic rays might be accelerated at the flanks of the heliosphere, the sides of the bubble rather than the nose. Voyager was traveling roughly toward the nose. If the flanks were the real acceleration zone, Voyager would have passed through the shock without seeing the peak. This would explain the data but created a new problem. No spacecraft has ever traveled toward the heliosphere's flanks. No mission is currently planned to do so. 22 years later, in 2026, the source of anomalous cosmic ray acceleration is still unidentified. The particles exist, the energies are measured, the acceleration is real, and we do not know where it happens. Voyager 2 added another complication 3 years later. On August 30th, 2007, the second probe crossed the termination shock at roughly 83.6 astronomical units. That is 10 astronomical units closer than Voyager 1's crossing. 10 astronomical units is about 930 million miles. The heliosphere was not just smaller than predicted, it was lopsided. Compressed on one side, pushed inward by forces the models had not accounted for. 2 crossings, 2 different distances. The first boundary already wrong in both location and behavior. And Voyager 1 was still more than a decade away from the heliopause, where the real surprises were waiting. There is a detail about Voyager, one that changes how the entire investigation unfolds. In 1980, during the Saturn flyby, the spacecraft's plasma science instrument failed. The plasma science experiment, called PLS, was the primary tool for directly measuring charged particle populations. It could count ions and electrons, determine their speeds, and calculate their temperatures. It was the instrument designed to characterize the heliopause crossing. It broke 32 years before the crossing it was built to detect. When Voyager 1 eventually reached the heliopause in 2012, it arrived without its most important sensor. Imagine investigating a crime scene without the ability to take fingerprints. You can still observe, still photograph, still measure other things. But the direct evidence you need most is the one thing you cannot collect. This left Donald Gurnett's plasma wave subsystem as the only instrument capable of indirectly measuring plasma density. The device weighs 1.4 kilograms, about the weight of a small hardcover book. It draws 1.6 watts of power, less than a nightlight. And NASA originally rejected it in the early 1970s. When Voyager's instrument suite was being selected, Gurnett proposed a full plasma wave receiver. NASA's review board said no. The spacecraft was already carrying too much weight. Gurnett came back with a compromise in 1973. He redesigned his instrument as a compact spectrum analyzer that could piggyback on the antennas already allocated to the planetary radio astronomy experiment. Share the antennas, save the weight, get the measurement. NASA accepted. The instrument that would eventually confirm humanity's first crossing into interstellar space almost did not fly. The plasma wave subsystem works differently from the plasma science instrument. PLS directly measures particles. PWS listens for waves. Specifically, it detects oscillations in the electric field caused by electrons vibrating in the surrounding plasma. The frequency of these oscillations depends on the density of electrons in the medium. Higher density means higher frequency. By measuring the frequency, you can calculate the density. By calculating the density, you can determine whether the spacecraft is surrounded by the thin solar wind plasma or the denser interstellar plasma. This distinction mattered because the heliopause was defined, in part, by a sharp jump in plasma density. On the solar side, the plasma is thin, dominated by particles blown outward from our star. On the interstellar side, the plasma is denser, composed of material that has nothing to do with our solar system. If Gurnett's instrument could detect that density jump through its frequency measurements, it could confirm the crossing even without PLS. But there was a problem. PWS can only measure plasma density when something disturbs the plasma enough to trigger detectable oscillations. In calm conditions, there is nothing to measure. The instrument sits silent, waiting for the medium to vibrate. This meant confirmation might not come at the moment of crossing. It might come weeks or months later, whenever a solar event sent a pressure wave rippling outward to reach Voyager's location and shake the local plasma into oscillation. The mission's most critical measurement would depend on a broken primary instrument, a rejected backup that weighed less than a bag of sugar, and the cooperation of the interstellar medium itself. Everything had to line up. And Voyager 1 was already inside the heliosheath, pushing through a region that looked nothing like what anyone expected. The heliosheath was supposed to be orderly. Models showed the solar magnetic field curving smoothly through this region, the field lines bending like the grain in polished wood as the solar wind decelerated and spread sideways after crossing the termination shock. Spacecraft would fly through a structured, layered environment where magnetic field direction changed gradually and predictably. Between 2007 and 2008, both Voyagers found something different. The heliosheath was filled with magnetic bubbles, not smooth curves. Bubbles, each one roughly 1 astronomical unit across about 93 million miles, the distance from Earth to our star. The magnetic field in the outer heliosphere was not flowing in orderly arcs. It was breaking apart through a process called magnetic reconnection, where field lines snap and reform into closed loops. The result was a churning froth of magnetic islands stretching across the entire outer boundary of the solar system. Picture it like this. You expected to find a neatly layered cake. Instead, you found a bathtub full of soap bubbles, each one the width of Earth's orbit around our star. This frothy structure had consequences for everything else. Cosmic rays, both the galactic variety coming from outside and the anomalous variety accelerated somewhere within the heliosphere, had to navigate this magnetic obstacle course. The bubbles could trap particles, redirect them, slow them down, or speed them up in ways no smooth field model could predict. The failure to find the anomalous cosmic ray peak at the termination shock suddenly had a possible contributing explanation. If the heliosheath was a maze of magnetic bubbles, the simple model of particles bouncing back and forth across a clean shock front was too naive. The bubbles also raised questions about how the heliosphere interacts with the interstellar medium at the heliopause. If the solar side of the boundary is a frothy mess rather than a smooth wall, the contact surface between solar and interstellar material might be irregular too. The clean, sharp heliopause of the textbooks was already looking suspect. Voyager 1 spent nearly 8 years crossing the heliosheath. The distance from the termination shock at 94 astronomical units to the heliopause at 121.6 astronomical units was about 27.6 astronomical units. At Voyager's speed of roughly 38,000 miles per hour, covering that distance took from December 2004 to August 2012. During those years, the magnetic bubble data accumulated, researchers published papers, models were revised, but the real test would come at the heliopause itself, where the solar magnetic field meets the interstellar magnetic field and the density of plasma jumps by an order of magnitude. Every model said that crossing would be unmistakable. The magnetic field direction should swing hard, like a compass needle whipping from north to east. Particle populations should flip, solar particles disappearing and galactic particles flooding in. The plasma density should jump sharply. All three signatures together would mark the boundary. Voyager 1 reached that boundary on August 25, 2012. The particle data cooperated. Solar particle counts dropped. Galactic cosmic ray counts surged. But the magnetic field did not swing. It barely shifted. The single most anticipated signature of the heliopause crossing, the one scientists had been waiting 35 years to see, did not materialize. And because it did not materialize, nobody could agree on what had just happened. On August 25, 2012, Voyager 1 was 121.6 astronomical units from our star. That is roughly 11.3 billion miles. The spacecraft had been flying for 35 years. Its radio signal, traveling at the speed of light, took 17 hours to reach Earth. The data it sent back showed two clear changes. Galactic cosmic ray intensity jumped to levels higher than any previous measurement in the mission's history. Solar energetic particle counts dropped to near zero. By these indicators alone, Voyager 1 had left the heliosphere and entered interstellar space. But NASA made no announcement, no press conference, no celebration. The reason was the magnetometer. The magnetic field strength had changed slightly at the boundary. The direction had not. Every model of the heliopause predicted that the solar magnetic field and the interstellar magnetic field would point in different directions. The transition from one to the other should produce a measurable swing in field orientation. Think of walking from a room where all the furniture faces north into a room where everything faces east. You would notice the change immediately. Voyager's magnetometer did not notice. The field on both sides of the crossing pointed in essentially the same direction. The difference was so small, it could barely be distinguished from instrument noise. Edward Stone, the project scientist who had led the mission since 1972, could not call the crossing without the magnetic signature. The particle data said Voyager had crossed. The magnetic data said it had not. And without the plasma science instrument, which had been dead since 1980, there was no direct plasma measurement to settle the question. This paralysis lasted for over a year. From August 2012 to September 2013, the status of Voyager 1 was officially ambiguous. The most distant human-made object had either entered interstellar space or it had not, and the two sets of instruments on board disagreed. The heliopause had been predicted at 150 astronomical units. Voyager had reached it at 121.6. The boundary was 20% closer than expected, and now the boundary itself was refusing to behave as modeled. Researchers published competing analyses. Conference presentations turned into arguments. The heliophysics community was split by a spacecraft that had done exactly what it was supposed to do. Except the boundary it crossed did not look like any model predicted. The missing magnetic flip was the expected definitive signature. Models had calculated the interstellar magnetic field direction based on the polarization of starlight, the structure of the local interstellar cloud, and the distribution of nearby stellar magnetic fields. The solar magnetic field direction was well known from decades of in situ measurement. The two should have been offset by a large angle. The fact that they were aligned raised a question that nobody could answer quickly. Were the models of the interstellar field wrong? Was the boundary doing something unexpected to the field? Or had Voyager not actually crossed the heliopause at all? For 13 months, the investigation stalled at this question, and the resolution, when it came, would depend entirely on the 1.4 kilogram instrument that NASA had almost rejected 40 years earlier. The scientific community did not wait politely for resolution. The debate over whether Voyager 1 had crossed the heliopause became one of the most public disagreements in space physics. Len Fisk and George Glockler, both established heliophysicists with decades of publications, argued that Voyager 1 had not entered interstellar space. Their interpretation was specific. The spacecraft had entered what they called a depletion region, a zone where solar energetic particles could escape along magnetic field lines, while the magnetic field itself remained solar in character. In their model, the particles left, but the field stayed. Voyager was still inside the heliosphere, just in an unusual corner of it. The argument was internally consistent. It explained the particle drop, it explained the unchanged magnetic field, and it kept the textbook model of the heliopause intact. On the other side was Donald Gurnett. He was not arguing, he was waiting. Gurnett's plasma wave subsystem needed the interstellar medium to vibrate. Without a disturbance, the instrument had nothing to measure. Throughout 2012 and into early 2013, the plasma around Voyager 1 was quiet. The PWS recorded steady, low-level data, no oscillation events strong enough to calculate electron density. Then, on April 9, 2013, the medium shook. A coronal mass ejection, a burst of solar plasma launched from our star months earlier, had finally traveled the 11 billion miles to Voyager's location. When it arrived, it compressed the surrounding plasma and triggered oscillations that the PWS could detect. The instrument recorded a plasma frequency between 2 and 3 kHz. This number carried the answer. In the thin solar wind plasma inside the heliosphere, plasma oscillation frequencies sit around 300 Hz. In the denser interstellar medium, the frequency should be much higher. The 2 to 3 kHz measurement corresponded to an electron density of roughly 0.08 particles per cubic centimeter. This was consistent with the predicted density of interstellar space. It was an order of magnitude higher than the solar wind density. Gurnett's team published their results in the journal Science. On September 12, 2013, NASA held the press conference. Voyager 1 had entered interstellar space on August 25, 2012. The confirmation came 13 months after the event, and it came from a 1.4 kilogram instrument drawing 1.6 watts of power, an instrument that existed only because its designer had agreed to a piggyback compromise 4 decades earlier. The Fisk and Gloeckler model was not technically disproven. Their interpretation was consistent with the magnetic data. But Gurnett's plasma density measurement placed the spacecraft firmly in interstellar plasma, and the density value was too high to be any form of solar wind, compressed or otherwise. The depletion region hypothesis could not account for the electron density. The community moved on, but the deeper question remained open. The magnetic field at the heliopause did not behave as predicted. The leading explanation was that the interstellar magnetic field drapes around the heliosphere like a bedsheet over a basketball, aligning itself along the contact surface. This draping effect could bring the two fields into rough alignment at the crossing point. It was a reasonable physical mechanism, but no model had predicted it before the crossing. It was retrofitted to explain the data after the fact. The heliopause was supposed to produce a clean magnetic signature. It produced the opposite, and the investigation into what the boundary actually looks like was only getting started. Edward Stone was 26 years old when he joined the Voyager project in 1972 as its project scientist. He would hold that role for 50 years, stepping down in 2022 at the age of 76. In that half-century, he coordinated 11 science teams through encounters with Jupiter, Saturn, Uranus, and Neptune. He served as director of the Jet Propulsion Laboratory from 1991 to 2001, overseeing 24 missions, including Mars Pathfinder and the Mars Exploration Rovers. He was also the principal investigator for the cosmic ray subsystem, the instrument that recorded the anomalous cosmic ray data at the termination shock. Stone was the person reporters called when Voyager data arrived. He was the voice that translated plasma density measurements and magnetic field vectors into language the public could understand. When Voyager 2 flew past Neptune in 1989, Stone was at the Jet Propulsion Laboratory. When Voyager 1's particle data shifted at the heliopause in 2012, Stone was the one who refused to announce the crossing until the evidence was complete. That caution, that insistence on waiting for Gurnett's plasma wave data before making a claim, cost NASA a year of headlines but protected the mission's scientific credibility. In June of 2024, Edward Stone died. He had heard his spacecraft reach interstellar space. He had watched the confirmation press conference in 2013. He had seen the data from Voyager 2's crossing in 2018. The mission he spent his professional life building was now outliving him. Suzanne Dodd took over as Voyager project manager in 2010, 2 years before the heliopause crossing. She led the team through both boundary crossings. The 2023 communications crisis, when Voyager 1 started transmitting gibberish, and the ongoing instrument shutdowns that are slowly blinding both spacecraft. Dodd once called the Voyagers deep space rock stars. She is now the person making the hardest decisions in the mission's history. Which instruments to turn off, which measurements to sacrifice, which eyes to close permanently as the power supply decays. The scale of Stone's tenure is difficult to communicate without a comparison. Consider that Stone joined Voyager the same year the Watergate break-in occurred. He was still running the project when the first iPhone shipped. The mission spanned the personal computer revolution, the internet age, the smartphone era, and the beginning of commercial spaceflight. Every year, Stone showed up and managed the data. His cosmic ray instrument delivered one of the mission's most disruptive findings at the termination shock. The failure of anomalous cosmic rays to peak where predicted was not a footnote. It invalidated the acceleration mechanism that Stone's own research community had developed over decades. The principal investigator's instrument disproved the principal investigator's field of study. Stone reported the result without commentary. Tom Crimigis, whose low-energy charged particles experiment flew past all 8 planets, watches as his instruments are powered down one by one. John Richardson, at the Massachusetts Institute of Technology, built the plasma science instrument on Voyager 2 that would later provide the only direct plasma measurements at the heliopause, data that Voyager 1 could never collect because of the 1980 failure. The human continuity of Voyager matters because spacecraft do not interpret data. People do. The debates, the arguments between Fisk and Gurnett, the decisions about which instruments to keep alive, all of these are human judgments made under uncertainty. Stone made those judgments for 50 years. Dodd makes them now, and the data that arrived after the heliopause crossing revealed an interstellar medium that no one had modeled correctly. The temperature of the local interstellar medium was predicted to fall between 15,000 and 30,000 degrees Kelvin. This range came from models of the local interstellar cloud, the patch of diffuse gas our solar system is currently traveling through. The models accounted for heating from nearby stars, cooling through radiation, and the general thermodynamic properties of low-density hydrogen and helium gas. 30,000 Kelvin was considered the upper bound. Most estimates clustered around 20,000. Voyager's instruments found temperatures between 30,000 and 50,000 Kelvin. At the low end, the measurement matched only the extreme edge of predictions. At the high end, it exceeded them by 67%. The interstellar medium, immediately outside our heliosphere, was significantly hotter than the consensus model allowed. The measurement is counterintuitive because the word temperature is misleading at these densities. Temperature in physics describes the average speed of particles. In the interstellar medium, the particles are moving fast. That gives a high temperature reading, but there are almost no particles. The density is roughly 1 atom for every 10 cubic inches of space. Compare that to the air in a typical room, which contains about 800 billion molecules per cubic inch. The interstellar medium is so empty that even at 50,000 Kelvin, you would freeze to death in seconds. The particles are fast, but there are not enough of them to transfer meaningful heat to anything. This distinction between temperature and heat matters because it affects how the heliosphere interacts with its surroundings. A hotter interstellar medium exerts more thermal pressure on the heliosphere's boundary. Higher pressure means the heliosphere gets compressed. This is one reason the termination shock and heliopause were both closer than predicted. The outside was pushing harder than anyone calculated. The source of the extra heat points beyond our solar system entirely. Our star sits inside a structure called the local bubble, a cavity roughly 300 light-years across that was carved out by supernova explosions over the past 10 to 20 million years. These explosions sent shockwaves through the interstellar medium, compressing gas, heating it, and leaving behind a hot, low-density environment. The elevated temperatures Voyager measured are not a local anomaly. They are the lingering signature of stars that exploded millions of years before our solar system existed in its current form. This connection between ancient supernovae and present-day measurements at the heliosphere's edge is one of the most underreported aspects of the Voyager findings. The boundary of our solar system is shaped by our star-blowing particles outward. It is also shaped by dead stars pressing inward. The heliosphere exists at the intersection of these two forces, and the balance between them determines where the boundaries sit, how thick they are, and whether the bubble we live in is expanding or contracting at any given moment. The 11-year solar cycle causes our star's output to fluctuate, pushing the heliopause outward during solar maximum and letting it contract during solar minimum. Researchers estimate the boundary shifts by 10 or more astronomical units over a full cycle. The heliosphere breathes, and the temperature of the surrounding medium determines how hard the outside pushes back during each contraction. Voyager measured the outside temperature, but it also began measuring density once it crossed the heliopause. And those density measurements would reveal something that still has no explanation, a trend that has been climbing for years and shows no sign of stopping. When Voyager 1 crossed the heliopause on August 25, 2012, it began measuring the density of interstellar plasma through its plasma wave subsystem. The initial readings placed the electron density at roughly 0.055 particles per cubic centimeter. This was in the expected range. Models of the local interstellar medium predicted densities somewhere between 0.04 and 0.07 particles per cubic centimeter at the heliopause. For once, a Voyager measurement landed where theory said it should. Then the density started rising. Over the following years, the electron density climbed to 0.12, then to 0.15 particles per cubic centimeter. That is nearly 3 times the initial measurement. Voyager was moving in a straight line through interstellar space at roughly 38,000 miles per hour, and the medium it was passing through kept getting denser. No model predicted this gradient. The interstellar medium was supposed to be roughly uniform at these scales, with density variations only over distances of light years, not the tens of astronomical units Voyager was covering. Starting around 2020, the density increase sharpened. Researchers identified what they called pressure front 2, a region where plasma density jumped by roughly 30% above the already elevated baseline and stayed elevated. As of early 2026, Voyager 1 has been inside this higher density zone for more than 5 years. The front shows no sign of ending. To understand why this is puzzling, consider the distances involved. 1 astronomical unit is about 93 million miles. Voyager 1 has traveled roughly 43 astronomical units since crossing the heliopause, approximately 4 billion miles through interstellar space. Over that distance, the density has nearly tripled. That is like walking across a football field and finding that the air pressure at the far end zone is 3 times higher than at the near end zone. with no wall or barrier in between. Something is compressing the interstellar medium in the region Voyager is entering, and the source of that compression is unknown. Several hypotheses exist. One is that Voyager is approaching a denser region of the local interstellar cloud, a natural variation in the patchy structure of gas between stars. Another is that a pressure wave from a distant source, perhaps related to the same supernova remnants that created the local bubble, is propagating through the medium. A third possibility is that the heliosphere itself is piling up interstellar material at its leading edge, the way a boat creates a bow wave in water. None of these explanations fully accounts for the duration and magnitude of the increase. Pressure front 2 has lasted longer than any transient event should at these scales. The data keeps arriving every 45 hours, and the trend keeps defying the models. The density measurements connect directly to the persistent hum Voyager detected starting in 2017. The hum is a narrowband plasma emission whose frequency correlates with local electron density. As the density rises, the characteristics of the hum shift. Together, they reveal that the interstellar medium has structure on scales of tens of astronomical units and pressure gradients that persist for years without explanation. Voyager 1 spent 6 years as the only human-made object in interstellar space. Then, in 2018, it got company, and what the second probe measured at the boundary did not match what Voyager 1 had found. The instrument Voyager 2 carried into interstellar space was called the Plasma Science Experiment, or PLS. It was built at the Massachusetts Institute of Technology under the direction of John Richardson. Its job was straightforward: point at incoming particles, measure their speed, temperature, and density. Voyager 1 had carried the same instrument once. It broke during the Saturn flyby in 1980, 32 years before the heliopause crossing it was designed to detect. Voyager 2 would not have that problem. On November 5, 2018, Voyager 2 crossed the heliopause at roughly 119 astronomical units from our star. Richardson's instrument recorded something definitive. The plasma density around the spacecraft jumped from roughly 0.002 particles per cubic centimeter to 0.039. That is a 20-fold increase. To put that in physical terms, imagine walking through a room where a single grain of sand floats in a volume the size of a shipping container, then crossing a doorway and finding 20 grains in the same space. Still almost nothing by earthly standards. But in the diffuse medium between stars, that jump is the equivalent of hitting a wall. The jump confirmed that Voyager 2 had crossed the heliopause. It was now the second human-made object in interstellar space. But the details of the crossing did not match what Voyager 1 had experienced 6 years earlier. Voyager 1 had crossed at 121.6 astronomical units. That is a difference of about 2.5 astronomical units, or roughly 230 million miles. The two spacecraft were traveling in different directions. Voyager 1 headed roughly toward the nose of the heliosphere, the direction our solar system plows into the interstellar medium. Voyager 2 traveled at a different angle, southward of the ecliptic plane. Models predicted that both crossings would look fundamentally similar because the heliopause was supposed to be a consistent boundary. It was not. Voyager 1 spent months in a strange transition zone where energetic particles dropped, but the magnetic field refused to change direction. Voyager 2 experienced something cleaner. The boundary was thinner. The plasma transition was sharper. The magnetic field shifted more noticeably, though still not as dramatically as decades of models had demanded. The heliosheath, the turbulent region between the termination shock and the heliopause, was also different for each probe. Voyager 1 traveled through roughly 27.6 astronomical units of heliosheath. Voyager 2 crossed about 35.4 astronomical units of it. That is nearly 8 astronomical units of difference, about 740 million miles. Same region, same boundary. Two fundamentally different experiences. Scientists had expected Voyager 2 to confirm what Voyager 1 had found. Instead, it contradicted it. The heliopause was not a uniform shell wrapped evenly around our star. It was uneven, thicker in some places, thinner in others, shaped by forces pressing in from outside. Two data points from two different directions painted two different pictures, and with no third spacecraft heading toward the boundary, there was no way to get a tiebreaker. The investigation had two witnesses. They disagreed, and the disagreement pointed to something larger than either crossing could explain on its own. The heliosphere itself was not the shape anyone had drawn. The asymmetry had shown up before Voyager 2 reached interstellar space. It appeared the moment Voyager 2 hit the termination shock. On August 30th, 2007, Voyager 2 crossed the termination shock at roughly 83.6 astronomical units. Voyager 1 had crossed the same boundary on December 16th, 2004 at 94.01 astronomical units. The difference was more than 10 astronomical units, about 930 million miles. That is roughly 10 times the distance from Earth to our star. The heliosphere was being squeezed unevenly. On one side, the termination shock sat closer. On the other, it pushed farther out. Something external was pressing harder on the southern flank. The interstellar magnetic field was the prime suspect. Measurements from both Voyagers indicated that the magnetic field, threading through the space between stars, was not uniform. It pressed against the heliosphere at an angle, compressing one side more than the other. The bubble our solar system blows into space was lopsided, like a balloon being pushed against a wall from one direction. In 2008, a year after Voyager 2's termination shock crossing, NASA launched a small spacecraft called the Interstellar Boundary Explorer, known as IBEX. It did not travel to the heliosphere's edge. Instead, it orbited Earth and pointed its detectors outward, catching energetic neutral atoms, or ENAs, flying inward from the boundary region. These atoms are created when charged particles from the solar wind exchange electrons with neutral interstellar atoms. They fly in straight lines, unaffected by magnetic fields, carrying information about conditions at the boundary back toward Earth, like messengers. IBEX found something nobody predicted. Across the sky, there was a narrow ribbon of intense, energetic neutral atom emissions. It formed a band roughly circular, stretched across the celestial sphere. No model had produced anything like it. The ribbon's location corresponded to where the interstellar magnetic field was perpendicular to the line of sight from Earth. That correlation was clear. The explanation was not. The IBEX ribbon meant the heliosphere's interaction with the interstellar medium was far more structured than anyone had modeled. The boundary was not a smooth compression zone, gradually transitioning from solar to interstellar material. It had features. It had concentrated regions of particle interaction that depended on the external magnetic field geometry. The interstellar medium was sculpting our bubble from the outside, combined with the 10 astronomical unit asymmetry in termination shock distance. The picture was becoming clear. The heliosphere was not a neat sphere, and it was not static. It was dynamic, asymmetric, and responsive to external forces that models had either underestimated or ignored entirely. The shape of our solar system's protective bubble depended as much on what lay outside it as on what our star pushed outward from within. The IBEX ribbon remains unexplained to this day. Multiple theories exist. One suggests the ribbon forms where neutral interstellar atoms are ionized by the solar wind, captured by the interstellar magnetic field, and then re-neutralized, sending energetic neutral atoms back toward Earth from a specific geometric configuration. Another proposes that the ribbon traces a region where the interstellar magnetic field drapes around the heliosphere and creates a secondary population of energetic particles. Neither model fully reproduces what IBEX observed. The ribbon was a discovery that generated more questions than it answered, and it pointed directly at a deeper problem. If the heliosphere was not a sphere, then what about the feature every textbook agreed on? What about the tail? For more than 50 years, every diagram of the heliosphere included a tail. It looked like a comet. Our star moved through the interstellar medium, and the solar wind streaming behind it was supposed to stretch into a long wake, extending hundreds of astronomical units downwind. The shape was intuitive. It matched what happens when you blow air into a moving stream. The front compresses, the back trails. Textbooks printed it, posters displayed it, animations rendered it. The comet tail heliosphere was one of the most recognizable images in space science. In 2017, data from the Cassini spacecraft killed it. Cassini spent 13 years orbiting Saturn, but one of its instruments, the ion and neutral camera, was pointed outward, catching energetic neutral atoms from the heliosphere's boundary, the same type of particles IBEX was designed to detect. Cassini had an advantage. It observed over a full 11-year solar cycle. That meant it could watch how the boundary responded to changes in solar output over time. When our star's activity increased, particles at the boundary should respond. The question was how fast that response traveled to different parts of the heliosphere. If there was a long tail, particles from the tail direction would take much longer to respond to solar changes. The signal would have to travel hundreds of astronomical units down the tail and then bounce back as energetic neutral atoms. There would be a measurable delay compared to particles arriving from the nose direction. Where the boundary was closer, there was no delay. Particles from the tail direction responded to solar changes just as fast as particles from the nose. The response was symmetric. Equal travel time from every direction meant equal distance in every direction. No long tail. The heliosphere was roughly the same size in all directions. Imagine expecting to find a river stretching behind a boat, and instead finding that the boat sits in the middle of a pond. The wake simply was not there. Merov Ofer and colleagues at Boston University proposed an alternative. Their magnetohydrodynamic simulations suggested the heliosphere might be shaped like a croissant, with two jets of material extending from the poles of our star's magnetic field, curling back on themselves. Not a sphere, not a comet, something stranger. The model fit some of the data, but not all of it. Other researchers proposed a more compact, roughly spherical shape. The debate remains open. What is not debated is that the tail is gone. 5 decades of textbook illustrations were wrong. The most basic geometric feature of the heliosphere, the one feature everyone agreed on, did not exist. Every space agency website, every introductory astronomy course, every documentary about the heliosphere had shown the same elongated shape with a streaming tail. All of them were depicting something that Cassini proved does not exist. The Cassini data was published just months before the spacecraft's deliberate destruction in Saturn's atmosphere in September 2017. One of its final scientific contributions was demolishing one of the oldest assumptions in heliophysics. And the loss of the tail had consequences beyond geometry. It changed the pressure balance. Without a long trailing wake dissipating solar wind energy downstream, more pressure had to be accounted for at the boundary itself. The energy that models had assumed was bleeding off into a tail was actually staying close to the heliosphere. The numbers were about to stop adding up. When physicists study a boundary between two different media, one of the first things they check is pressure balance. The pressure pushing outward from inside must roughly equal the pressure pushing inward from outside, or the boundary moves. At the heliopause, outward pressure comes from the solar wind, its embedded magnetic field, and energetic particles like cosmic rays. Inward pressure comes from the interstellar plasma, its magnetic field, and whatever else exists in the local interstellar medium. Scientists added up every known source of pressure on both sides. The numbers did not balance. The total measured pressure at the heliosphere's edge was higher than any model predicted. There was more pressure pushing inward than the known components of the interstellar medium could account for. Something was missing from the equation. An unknown pressure source was acting on the boundary, and nobody could identify what it was. This was not a small discrepancy. IBEX data showed that the total pressure at the heliopause was roughly 25 to 50% higher than models produced using all known factors. That is equivalent to an entire additional pressure component the size of the thermal plasma contribution just unaccounted for. Imagine building a dam, calculating the water pressure on one side and the structural resistance on the other, and finding that the dam holds firm even though your equations say it should have burst. Something you have not measured is reinforcing the structure. Several hypotheses exist. Some researchers suggest the interstellar magnetic field is stronger than current measurements indicate, providing additional magnetic pressure. Others point to populations of energetic particles in the interstellar medium that current instruments cannot detect. A third possibility involves the structure of the interstellar medium itself. Voyager 1's density measurements showed plasma density rising steadily after the heliopause crossing, from 0.055 particles per cubic centimeter to values between 0.12 and 0.15. Starting around 2020, Voyager 1 entered a region researchers call Pressure Front 2, where density jumped an additional 30% and stayed elevated for more than 5 years. No model predicted this region. No explanation has gained consensus. The pressure imbalance connects to every other anomaly. The missing tail means more energy stays near the boundary. The asymmetric shape means pressure is distributed unevenly. The porous heliopause, which the next crossing would reveal, means material leaks across the boundary, further complicating the accounting. This is not a situation where one measurement was slightly off. The entire framework for understanding the heliosphere's pressure environment was incomplete. Every boundary condition scientists had used to model the heliosphere relied on assumptions about external pressure that turned out to be wrong. The termination shock was in the wrong place because the external pressure was higher than expected. The heliopause was closer than predicted for the same reason. The shape was wrong because the pressure was not uniform. And now the total pressure budget had a hole in it that no known component could fill. Something out there, in the interstellar medium surrounding our solar system, was exerting force that we could measure in its effects, but could not identify at its source. The boundary was holding. The math said it should not be. And Voyager 2's plasma instrument was about to reveal another reason the old model could not survive. The textbook version of the heliopause was clean. On one side, solar wind. On the other side, interstellar plasma. A sharp line. Cross it and you leave our star's domain entirely. That was the prediction. Voyager 2's plasma science instrument found something different. As the spacecraft approached and then crossed the heliopause in November 2018, Richardson's instrument detected solar wind particles beyond the boundary. Material from our star was leaking into interstellar space. The wall had holes. This was not entirely surprising in retrospect. Voyager 1 had hinted at something similar 6 years earlier, though it lacked the instrument to measure it directly. In the months before Voyager 1's confirmed crossing, the spacecraft entered a bizarre transition region that scientists named the magnetic highway. In this zone, energetic solar particles dropped sharply while galactic cosmic rays surged. But the magnetic field did not change direction. The field lines remained solar in character, connected back to our star, even as the particles riding those field lines were interstellar. Picture a highway running along a national border. The road belongs to one country, but the cars on it come from the other side. The infrastructure is solar. The traffic is interstellar. Particles from outside were streaming inward along magnetic field lines that originated from our star, while solar particles escaped outward along the same paths. The boundary was not a wall. It was something more like a membrane, selectively permeable in both directions. Voyager 2's direct plasma measurements confirmed and extended this picture. The transition at the heliopause was not instantaneous. There was a mixing layer where solar and interstellar plasmas coexisted. The boundary had thickness. It had structure. Solar material did not simply stop at the edge. It leaked through, carried along magnetic field lines that draped across the heliopause like cloth over a frame. The technical term for this is heliopause porosity. The boundary allows material to pass through in ways that depend on the local magnetic field geometry. Where field lines connect across the boundary, particles flow. Where they do not, the boundary holds. The result is a patchy, inconsistent border that varies from location to location and probably from year to year as the magnetic field configuration shifts with the solar cycle. This porosity has consequences. If solar material leaks outward, it carries energy and momentum with it, affecting the pressure balance at the boundary. If interstellar material leaks inward, it changes the composition of the outer heliosphere. The clean two fluid model, solar wind inside, interstellar plasma outside, was too simple. Reality was a mixed zone where the two media interpenetrated. The porosity also raised a question about protection. The heliosphere shields the inner solar system from a significant fraction of galactic cosmic radiation. If the boundary leaks, that shielding is not absolute. The degree of leakage, how it varies with location and solar cycle, and whether it affects the radiation environment deeper inside the heliosphere are all open questions. Voyager 2 measured only one point on a boundary that wraps around the entire solar system, with the boundary revealed as porous, the heliosphere as a shape unknown, and the pressure equations unbalanced. The investigation needed something the Voyagers could not provide. It needed a global view, a way to see the entire heliosphere at once rather than sampling it along two thin lines. But before that new tool could arrive, the investigation had one more surprise waiting in the data. Voyager 1 had been quietly collecting since 2017. The interstellar medium was not silent, it was humming. In Chapter 1, there was a sound, a persistent, narrowband plasma emission detected by Voyager 1's plasma wave subsystem beginning in 2017. At the time, it was a teaser, an unexplained signal from interstellar space. Now, with the full context of what Voyager has found, that sound becomes something more significant. The emission sits at a frequency corresponding to the local electron density in the interstellar medium, roughly 0.11 particles per cubic centimeter. The bandwidth is narrow, about 0.04 kHz wide. It is continuous. It does not start and stop with solar events. It does not correlate with anything our star does. It is a feature of the interstellar medium itself, a background tone in the space between stars that nobody predicted would exist. Before Voyager crossed the heliopause, the consensus was straightforward. The interstellar medium near our solar system was cold, sparse, and quiet. Models placed the temperature at 15,000 to 30,000 kelvins. The density was low, the magnetic field was weak. There was no reason to expect activity, structure, or sound. The region was supposed to be the cosmic equivalent of an empty room. Voyager found a concert hall. The plasma temperature measured between 30,000 and 50,000 kelvins, up to 67% hotter than the upper end of predictions. The density was higher than expected and kept climbing, and the hum was there, persistent, steady, the acoustic signature of a medium that was anything but quiet. Analysis of the hum by Stella Koch-Ocker and colleagues revealed something deeper. The density fluctuations encoded in the signal followed a pattern called the Kolmogorov turbulence spectrum. This is a specific mathematical relationship between the size of turbulent eddies and their energy, first described by the Russian mathematician Andrei Kolmogorov in 1941. When a fluid is turbulent, energy cascades from large scales down to small scales in a predictable way. The interstellar medium near our solar system follows this cascade. It has turbulence on scales of astronomical units, the same unit of distance that measures the gap between Earth and our star. Think of it like holding a stethoscope against the wall of a building and hearing the plumbing. You cannot see the pipes. You do not know the layout. But the sound tells you there is a system, there is flow, there is structure. The interstellar hum is Voyager's stethoscope pressed against the medium between stars, and what it hears is not emptiness. It is a fluid in motion, stirred by forces operating on scales far larger than our heliosphere. Those forces almost certainly trace back to ancient supernovae. Our solar system sits inside the local interstellar cloud, which itself occupies a larger structure called the local bubble, a cavity roughly 300 light-years across, carved out by stellar explosions over the past 10 to 20 million years. The heat, the density fluctuations, the turbulence encoded in the hum are all fingerprints of dead stars. Energy deposited millions of years ago, still rippling through the medium surrounding our solar system. The quiet void that scientists expected was never quiet. It was never a void. And the instrument that detected this, Donald Gurnett's 1.6-watt plasma wave subsystem, had been listening since 1977, waiting 40 years for something worth hearing. In late 2023, that instrument nearly went silent for good, not because it failed, because the spacecraft carrying it started sending gibberish. On a day in November 2023, the data stream from Voyager 1 changed. Where there had been ordered science telemetry, there was now noise, repeating patterns of ones and zeros that encoded nothing. The most distant human-made object, 15 billion miles from Earth, was talking, but it was no longer making sense. The problem was in the Flight Data Subsystem, or FDS. This is the spacecraft's central computer. It collects data from all active instruments, packages it into telemetry frames, and sends it to the transmitter for relay back to Earth. Every piece of science Voyager 1 had returned since 1977 passed through this system. The FDS runs on memory chips, fabricated in the mid-1970s. Its total memory capacity is 69.63 kilobytes. For comparison, a single photograph on a modern smartphone uses roughly 3 to 5 megabytes. The FDS has less memory than the text of a short novel. One of those memory chips had failed. Engineers at the Jet Propulsion Laboratory determined that approximately 3% of the FDS memory was corrupted. That may sound minor, but 3% of 69.63 kilobytes is not a lot of room, and the code stored in that region was essential for packaging telemetry. Without it, the FDS could not assemble coherent data frames. Science stopped. Engineering telemetry stopped. For 5 months, Voyager 1 transmitted meaningless signals across 15 billion miles of space. The challenge facing the engineering team was unlike any repair in the history of spaceflight. The spacecraft was farther from Earth than any object humans have ever built. A radio signal traveling at the speed of light takes about 22.5 hours to reach it. That means every command sent from Earth requires a 45-hour round trip before engineers can see the result. There is no real-time interaction, no joystick, no video feed. Every action is a letter sent across the solar system with a day-long wait for the reply. The code they needed to fix was 46 years old. It was written for hardware that no longer exists on Earth. The documentation, where it survived, described systems designed by engineers who had long since retired or died. Suzanne Dodd's team at the Jet Propulsion Laboratory had to read through archival code listings, understand the original logic, and figure out how to work around a physical hardware failure in a computer smaller than a modern calculator, from a distance that light itself needs nearly a full day to cross. Imagine trying to fix a typewriter. The typewriter is in a locked room. You cannot enter the room. You can only slide notes under the door and wait 22 hours for a response. The typewriter was built in 1977. You have the original manual, but some pages are missing, and 3% of the typewriter's keys are jammed in positions that produce the wrong letters. That is approximately what the Voyager engineering team faced, except the room was 15 billion miles away, and the typewriter was the only one of its kind in existence. The team needed a way to see what was broken before they could fix it. In early 2024, they designed a plan. They would send a single command to Voyager 1, a diagnostic prompt. Engineers called it a poke. On March 3rd, 2024, the command left Earth. It traveled at the speed of light across the inner solar system, past the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune, through the Kuiper belt, across the termination shock, through the heliosheath, past the heliopause, and into interstellar space. 22.5 hours later, it arrived at Voyager 1. The poke command instructed the flight data subsystem to dump its entire memory contents back to Earth. Not interpreted data, not packaged telemetry, just the raw contents of every memory address, corrupted or not. The spacecraft complied. 22.5 hours after that, the memory dump arrived at the Deep Space Network antennas in California. Engineers now had a complete map of the damage. They could see exactly which memory addresses held corrupted data and which were still functional. The corrupted chip held about 3% of the total memory, and the code stored there was critical for assembling telemetry frames. The data from every instrument passed through routines stored on that chip. With those routines corrupted, nothing could get out cleanly. The solution was not to fix the chip. You cannot repair a semiconductor from 15 billion miles away. Instead, the team decided to move the affected code to other locations in memory where functional chips still had available space. This is roughly equivalent to discovering that one shelf in a library has collapsed, and rather than repairing the shelf, you redistribute the books across every other shelf that has room. The challenge was that the code had to work from its new locations. Memory addresses were hard-coded into the software. Subroutines referenced specific locations. Moving the code meant rewriting the address references so the system could find what it needed in unfamiliar places. Between April 18th and 20th, 2024, the team uploaded the relocated code. Each upload was a carefully constructed set of commands sent across the solar system and verified after the 45-hour round trip. There was no room for error. A bad command could crash the FDS entirely, potentially ending the mission. The team sent the patches in small pieces, confirming each one before sending the next. On April 20th, engineering telemetry returned. The data was clean. The FDS was assembling coherent frames again, routing around the dead chip the way a highway routes around a collapsed bridge. Engineers spent the following weeks verifying each instrument's data stream. On May 19th, 2024, full science data transmission resumed. Voyager 1 was back. The repair took roughly 5 months from the onset of gibberish to the restoration of science. It was performed on a computer with less memory than a modern greeting card, running code written during the Carter administration, from a distance so great that the engineers could not have a conversation with their own spacecraft. Each exchange was a monologue followed by a day of silence. Suzanne Dodd later described the Voyagers as deep space rock stars. The description is apt, but it understates the fragility. The FDS crisis revealed what everyone already knew but preferred not to discuss. Voyager 1 is old. Its hardware is degrading. The corrupted memory chip will not be the last failure. And every year, the power situation gets worse. The repair saved the mission, but it also served as a reminder that the clock was running and it was not slowing down. Both Voyager spacecraft run on radioisotope thermoelectric generators, or RTGs. These devices convert the heat from decaying plutonium-238 into electricity. There are no moving parts, no chemical reactions, just the steady, inevitable decay of radioactive material producing warmth, which thermocouples convert into electrical current. When the Voyagers launched in 1977, each spacecraft's RTGs produced about 470 watts of electrical power. That was enough to run all 11 scientific instruments, the communications system, the onboard computers, and the heaters that keep the spacecraft's fuel lines from freezing. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half the remaining plutonium has decayed. The power output drops accordingly, declining at roughly 4 watts per year. By early 2026, each spacecraft generates somewhere around 220 watts. That sounds like a reasonable amount until you consider that it must power everything, and everything includes heaters for fuel lines that would freeze solid without them, a transmitter that broadcasts across 15 billion miles, computers that manage attitude control and data processing, and whatever scientific instruments are still active. The math is unforgiving. 4 watts lost per year means roughly one instrument's worth of power disappears every couple of years. Suzanne Dodd and her team at the Jet Propulsion Laboratory face a decision that no other mission team has confronted in quite this way. They must choose which instruments to kill. The decisions have already begun. In September 2024, Voyager 2's plasma science instrument was powered down. This was the same instrument that provided the only direct plasma measurements at the heliopause, John Richardson's device from MIT, the one that recorded the 20-fold density jump in November 2018. That capability is now gone permanently. No other spacecraft carries a plasma instrument heading toward interstellar space. That measurement will not be repeated. In February 2025, Voyager 1's cosmic ray subsystem was turned off. This was Edward Stone's instrument, the one he served as principal investigator for across the entire mission. It detected the anomalous cosmic ray surprise at the termination shock in 2004. It measured the surge in galactic cosmic rays that signaled the heliopause crossing in 2012. It is now silent. In March 2025, Voyager 2's low-energy charged particles instrument followed. Tom Crimigis built that instrument. He is the only scientist in history to have constructed instruments that flew to all 8 planets in our solar system. His experiment on Voyager 2 is now dark. By the end of 2026, each Voyager will likely carry only 2 or 3 active instruments. The magnetometer and the plasma wave subsystem are the most power-efficient instruments on both spacecraft. They draw the least current and return the most scientifically valuable data. They will be the last to go. Engineers estimate they may survive into the early 2030s. After that, there will not be enough power to run anything. The transmitters will fall silent, the data will stop, and 2 spacecraft will continue drifting through interstellar space, intact but mute, carrying golden records that nobody will play for millions of years. But before that silence arrives, Voyager 1 had one more trick in its aging hardware. In October 2024, Voyager 1 stopped responding on its primary X-band transmitter. Commands from Earth went unanswered. The Deep Space Network antennas listened and heard nothing on the expected frequency. For a mission that had just survived a 5-month computer crisis, this looked like it might be the end. Then engineers found the signal. It was broadcasting on S-band. S-band is a lower frequency radio channel that Voyager 1 had not used since 1981. 43 years earlier, during the Saturn encounter, the spacecraft had switched to X-band as its primary communications link because X-band offers higher data rates and better performance over extreme distances. The S-band transmitter was left powered but dormant, a backup that nobody expected to need again. Something triggered Voyager 1 to switch back. The exact cause is still under investigation, but the likely explanation involves the spacecraft's fault protection software. When Voyager detected an anomaly with the X-band system, its onboard logic automatically switched to the backup. The same logic that was written in the 1970s, the same code that engineers had just finished patching around corrupted memory chips, made a decision on its own from 15 billion miles away. It chose to survive. The S-band signal was weak. S-band transmits at a lower power and lower frequency than X-band, which means the signal spreads more and arrives at Earth with less energy. The Deep Space Network had to use its largest antennas, the 70-meter dishes. and integrate the signal over longer periods to pull coherent data from the noise. But the data was there. Voyager 1 was talking. It had simply switched to a voice nobody had listened for in 4 decades. Consider what this means in engineering terms. A radio transmitter built in the mid-1970s, installed on a spacecraft that launched in 1977, left unused for 43 years, while the spacecraft traveled from Saturn to interstellar space, exposed to the radiation environment of the outer solar system and beyond, powered up and transmitted a coherent signal across 15 billion miles. The engineering margins built into Voyager's hardware in the 1970s are still paying dividends half a century later. Engineers re-established full communication and sent commands to switch Voyager 1 back to X band. By November 2024, the spacecraft was back on its primary transmitter. The S-band system returned to dormancy, having performed exactly the function it was designed for 4 decades late. The Ghost Transmitter episode is minor compared to the FDS crisis or the heliopause crossing. No new science came from it. No models were overturned. But it captures something about the Voyager mission that the science alone does not convey. These spacecraft were built with margins that their designers could not have imagined would matter. Nobody in 1977 planned for a 43-year transmitter dormancy test. Nobody designed the fault protection software expecting it to make autonomous decisions from interstellar space. The engineering was built to be robust, and that robustness has outlasted every prediction about the mission's lifespan, the heliosphere's boundaries, and the interstellar medium's properties. The hardware keeps working, the physics keeps surprising, and somewhere between those two facts, the investigation continues. With instruments shutting down and power fading, what remained to be learned depended entirely on what the last instruments could still detect: the magnetometer and the plasma wave subsystem. Those are the 2 instruments that will outlast everything else on both spacecraft. They draw the least power, they weigh almost nothing, and they happen to be the 2 instruments still capable of answering the questions that matter most. The magnetometer measures the strength and direction of the magnetic field. The plasma wave subsystem listens for oscillations in the charged gas surrounding the probe. Between them, they can still detect the interstellar hum, track density changes in the medium, and map the structure of the magnetic field stretching through interstellar space. On paper, 2 instruments sounds like the end of an investigation. In practice, these 2 instruments just delivered a result that overturned one of the last surviving predictions about the heliopause. For decades, models assumed that the solar magnetic field and the interstellar magnetic field would point in different directions. That difference was supposed to be the clearest marker of the boundary. When Voyager 1 crossed the heliopause in 2012, the expected directional shift never appeared. Scientists debated for a year about whether the crossing had even happened. At the time, the missing flip was treated as a puzzle, a local anomaly, something to explain away. It is not a local anomaly. With years of magnetometer data from both probes now in hand, the picture is clear. The local interstellar magnetic field exceeds 3 nanoteslas, stronger than predicted, and it is closely aligned with the solar magnetic field across the heliopause. The 2 fields, generated by completely different sources separated by billions of miles, point in nearly the same direction. Nobody predicted this. Nobody can fully explain it. 3 nanoteslas is a weak field by everyday standards. A refrigerator magnet produces a field roughly 10 million times stronger, but in the diffuse space between stars, 3 nanoteslas is significant. It means the interstellar medium is exerting more magnetic pressure on the heliosphere than models assumed. And the alignment means the boundary between solar space and interstellar space is not the sharp magnetic discontinuity that 50 years of theory demanded. The boundary is magnetically smooth. That smoothness is exactly why it took a year to confirm Voyager 1 had crossed it. The smoking gun everyone was looking for The dramatic field reversal does not exist because the fields on both sides happen to agree. Whether this alignment is a coincidence of our local galactic neighborhood or evidence of a deeper physical connection remains an open question. Some researchers propose that the interstellar field is draping around the heliosphere, aligning itself through pressure interactions at the boundary. Others argue the alignment may be specific to the local interstellar cloud, the particular patch of galactic gas our solar system is currently passing through. The data cannot yet distinguish between these possibilities. The heliosphere is not sitting inside a random magnetic environment. It is embedded in a field that mirrors its own. And the instrument that confirmed interstellar crossing, the plasma wave subsystem that NASA almost rejected in 1973, continues to detect the hum that started in 2017. The hum has not stopped. The density fluctuations have not stabilized. The interstellar medium is still talking, and the last two instruments on each probe are still listening. But Voyager was never designed to map the heliosphere from the outside. It was designed to fly through it. For a global picture, the investigation needed something else entirely. On September 24, 2025, a Falcon 9 rocket lifted off carrying the Interstellar Mapping and Acceleration Probe. The spacecraft arrived at the first Lagrange point on January 10, 2026, parking itself roughly 1 million miles from Earth, where the gravitational pull of our planet and our star balance out. On February 1, 2026, primary science operations began. After nearly 50 years of relying on two probes flying along two thin lines through the heliosphere, the investigation finally gained a tool that could see the whole structure at once. The Interstellar Mapping and Acceleration Probe carries 10 instruments, with 15 to 35 times greater sensitivity than its predecessor, the Interstellar Boundary Explorer, which launched in 2008. Where the Interstellar Boundary Explorer gave scientists a blurry snapshot of energetic neutral atoms streaming back from the heliosphere's edge, the new probe will produce detailed maps with enough resolution to track changes over months instead of years. Energetic neutral atoms are the key. When charged particles from the solar wind collide with neutral atoms in the interstellar medium near the heliosphere's boundary, some of those particles steal an electron, become electrically neutral, and fly in a straight line back toward Earth. By measuring where these atoms come from, how fast they travel, and what species they are, scientists can reconstruct what is happening at the boundary without sending a spacecraft there. Think of it like hearing a battle from miles away by listening to the sound. You cannot see the field, but you can map what is happening based on what reaches you. The Interstellar Boundary Explorer had already proven this technique works. Its biggest discovery was the ribbon, an unexpected band of energetic neutral atom emissions forming a narrow arc across the sky that no model had predicted. The ribbon appears to trace where the interstellar magnetic field is perpendicular to our line of sight, but its exact origin is still debated. The new probe will observe the ribbon at far higher resolution and across a wider energy range, potentially resolving whether it originates at the heliopause, beyond it, or through some interaction between the two regions. But the probe's most important contribution may be something simpler than solving the ribbon. It will produce the first three-dimensional maps of the heliosphere. Every conclusion drawn from Voyager data comes with the same caveat. Two flight paths through a three-dimensional structure cannot tell you the shape of that structure. It is like drilling two core samples through a mountain and trying to describe the entire mountain from what you pull out of two holes. The probe changes that. By collecting energetic neutral atoms from every direction simultaneously, and by tracking how those emissions change as our star's output varies over its 11-year cycle, the mission can build a global picture of the heliosphere's size, shape, and dynamics. The first full sky maps are expected later in 2026. When they arrive, they will either confirm or contradict the competing models that have been arguing with each other since Voyager crossed the boundary. The Voyager probes are still out there, still measuring from inside interstellar space. The new probe is watching from near Earth. For the first time, the investigation has both a ground-level view and an aerial view of the same structure. The question is whether the two views will agree. As of early 2026, we do not know the shape of our own heliosphere. The comet tail model is dead. Cassini killed it in 2017, with neutral atom data showing that particles from the supposed tail direction responded to changes in solar output just as quickly as particles from the nose. No time delay means no extended tail. 50 years of textbook illustrations showing a long windsock trailing behind our solar system were wrong. But what replaced the tail is not settled. A simple sphere does not work either. Voyager 2 crossed the termination shock at 83.6 astronomical units. Voyager 1 crossed it at 94. That 10 astronomical unit difference, roughly a billion miles, proves the heliosphere is being squeezed unevenly. The interstellar magnetic field presses harder on one side than the other. In 2016, Merov Ofer and colleagues at Boston University proposed a shape nobody expected. Using magnetohydrodynamic simulations, they argued the heliosphere might resemble a croissant, with two lobes of solar magnetic field jutting out from opposite sides, while the middle pinches inward. The model is driven by the behavior of the solar magnetic field as it twists and folds in the outer heliosphere, creating two distinct jets of magnetized plasma. The croissant fits some observations. It explains the asymmetry between the two Voyager crossings. It accounts for certain features in the Interstellar Boundary Explorer ribbon data, but it does not match everything. Other groups have proposed shapes closer to a deflated beach ball, compressed on one side and bulging on the other, with the interstellar magnetic field imposing the distortion from outside. The Interstellar Boundary Explorer revealed that the heliosphere's boundary is tilted roughly 30 degrees from what models assumed, and that the tilt shifts by more than 10 astronomical units as the solar cycle waxes and wanes. The heliosphere breathes. It expands during solar maximum, when our star's output is strongest, and contracts during solar minimum, when the wind weakens. A beach ball, inflating and deflating by a billion miles every 11 years. That breathing cycle means the heliopause is not in a fixed location. It is a moving target. Voyager 1 and Voyager 2 each captured a single snapshot of a boundary that shifts constantly. The location each probe crossed tells you where the boundary was on that particular day, in that particular direction, during that particular phase of the solar cycle. Extrapolating from those two snapshots to a permanent shape is exactly the kind of assumption that has been wrong at every step of this investigation. The interstellar mapping and acceleration probe was built to resolve this. Its sky maps will show the global distribution of energetic neutral atoms at different energies, which corresponds to different distances and processes at the boundary. Over time, as the solar cycle progresses, those maps will reveal how the shape changes. Whether the heliosphere is a croissant, a squashed sphere, or something nobody has proposed yet depends on data that does not exist until the probe delivers it. We live inside this structure. It shields us from a significant fraction of galactic cosmic radiation. It determines how much of the galaxy's energy reaches the inner planets, and after nearly 50 years of direct exploration, we still cannot draw it. The anomalous cosmic ray problem is now 22 years old and counting. When Voyager 1 crossed the termination shock in December of 2004, the single most confident prediction in heliophysics collapsed. Anomalous cosmic rays, particles that originate as neutral atoms drifting into the heliosphere, get ionized by solar radiation and are then accelerated to enormous energies, were supposed to reach peak intensity right at the termination shock. That was the whole model. The shock was the accelerator. Voyager 1 would fly through it and measure the peak. The peak was not there. Anomalous cosmic ray intensity did not spike at the termination shock. It kept rising as Voyager 1 moved deeper into the heliosheath, the turbulent region between the shock and the heliopause. The instrument designed to detect this peak, the cosmic ray subsystem built under Edward Stone's direction, recorded a smooth increase with no sign of the expected maximum. Voyager 2 confirmed the same pattern 3 years later at its own shock crossing. No peak, just a steady climb. Entire research programs had been built on the prediction that the termination shock accelerates anomalous cosmic rays. Doctoral theses, simulation codes, funding proposals. The mechanism seemed so straightforward. Neutral atoms drift in. They get ionized. The solar wind carries them outward. They hit the shock and bounce back and forth across it, gaining energy with each crossing. A process called diffusive shock acceleration. It works for other astrophysical shocks. It was supposed to work here. It did not. The current leading hypothesis is that anomalous cosmic rays are not accelerated at the nose of the heliosphere where both Voyagers crossed. They may be accelerated at the flanks, the sides of the heliosphere where the termination shock curves away from the direction of travel through the galaxy. At the flanks, the geometry of the shock is different. The magnetic field meets it at a different angle. The acceleration conditions may be more favorable there. But no spacecraft has ever visited the heliosphere's flanks. Both Voyagers flew roughly toward the nose. Every direct measurement of the termination shock comes from the front of the structure, not the sides. Imagine investigating a building fire, but only being allowed to look through the front door. You can describe what the lobby looks like. You cannot tell someone what happened in the back rooms. The interstellar mapping and acceleration probe may offer indirect evidence. Its energetic neutral atom detectors can measure particles arriving from every direction, including the flanks. If anomalous cosmic rays are being accelerated there, some fraction of the resulting energetic neutral atoms should be visible in the probe's sky maps. But indirect evidence is not the same as flying through the region and measuring the particles directly. The acceleration source for anomalous cosmic rays remains one of the oldest open questions in heliophysics. We know the particles exist. We measure them constantly. We have tracked their intensity across 2 shock crossings and through the heliosheath and into interstellar space. And we still do not know where they get their energy. The termination shock, the structure that was supposed to answer this question, turned out to be the wrong answer. 22 years later, the right answer has not arrived. And the instrument that first measured the problem on Voyager 1, the cosmic ray subsystem, was powered off in February 2025. The clock on solving this one just got shorter. If you lined up every unresolved question Voyager has generated and pinned them to a wall, the board would look like the evidence room of a case that keeps getting more complicated. 7 open investigations, none of them closed, all of them connected. Start with Pressure Front 2. Since roughly 2020, Voyager 1 has been passing through a region of interstellar space where the plasma density is 30% higher than the surrounding medium. This elevated density has persisted for more than 5 years. No model predicted it. No definitive explanation exists. Something in the interstellar medium is compressing the plasma along Voyager 1's path, and we do not know what. Second, the magnetic field alignment. Solar magnetic field lines generated by our star and interstellar magnetic field lines generated by galactic processes should not point in the same direction. They do. Across the heliopause, the 2 fields are closely aligned. Whether this is a local coincidence or a sign of a deeper physical connection remains unanswered. Third, the interstellar hum. Continuous narrowband plasma emission detected since 2017. Not tied to any solar event, not pulsed or periodic. A constant low-frequency signal revealing density fluctuations over distances of 10 or more astronomical units. What drives it and whether it is uniform across the interstellar medium or specific to Voyager 1's path is unknown. Fourth, the anomalous cosmic ray acceleration source, predicted at the termination shock. Not found there, possibly at the flanks, Unconfirmed, 22 years without an answer. Fifth, heliopause porosity. Voyager 2's plasma instrument detected solar particles leaking beyond the heliopause into interstellar space. The boundary is not sealed. Material crosses in both directions. How much leaks through, over what area, and what effect this has on the interstellar medium near our solar system are all open questions. A border that leaks is fundamentally different from a border that does not, and the difference matters for understanding how much galactic cosmic radiation reaches the inner solar system. Sixth, the shape of the heliosphere. Bubble, croissant, deflated sphere, no consensus. Two Voyager trajectories cannot resolve a three-dimensional shape. The interstellar mapping and acceleration probe may settle this within a few years, or it may reveal a shape more complex than any current model. Seventh, the outer heliosphere, pressure imbalance. When researchers add up every known pressure source at the heliosphere's boundary, magnetic pressure, thermal plasma pressure, cosmic ray pressure, and RAM pressure, the total exceeds what models predict. There is an unidentified component. Something is pushing on the boundary from outside, and the measurements confirm the push without identifying the pusher. Picture a sealed room where you can measure the air pressure against every wall, and the numbers are higher than what the known air supply can account for. There is pressure from somewhere, and you cannot find the source. 7 cases, all opened by Voyager data, none closed by Voyager data. The probes were never designed to solve these problems. They were designed to fly past the outer planets and keep going. The fact that they survived long enough to reach interstellar space is an engineering accident that became the most productive accident in the history of space exploration. But productive is not the same as conclusive. Every one of these 7 questions points outward toward a galactic environment that we have barely begun to map. Pull back far enough, and the heliosphere is not floating in empty space. It is embedded inside a structure called the local interstellar cloud, a patch of warm, partially ionized gas roughly 30 light-years across. Our solar system entered this cloud sometime in the last few thousand to tens of thousands of years and will exit it eventually. Beyond the local interstellar cloud sits a much larger structure, the local bubble, a cavity in the interstellar medium roughly 300 light-years in diameter. The local bubble was carved by a series of supernova explosions over the past 10 to 20 million years. Massive stars in the solar neighborhood exhausted their fuel, detonated, and the blast waves swept the surrounding gas outward, hollowing out a region of unusually low density and high temperature. Our solar system sits near the edge of this cavity. The hot interstellar medium that Voyager measured, 30,000 to 50,000 Kelvin instead of the predicted 15,000 to 30,000, makes more sense in this context. The gas outside the heliosphere is not just interstellar gas. It is gas that has been heated and processed by stellar explosions that happened millions of years before our species existed. The density fluctuations that produce the interstellar hum, the pressure anomalies that nobody can account for, the magnetic field structures that do not match simple models, all of it may be the lingering fingerprint of dead stars. Consider the scale. A supernova releases roughly as much energy in a few seconds as our star will produce over its entire 10 billion year lifetime. That energy does not just vanish. It propagates through the interstellar medium as shockwaves, heats the surrounding gas, compresses magnetic field lines, and creates turbulence that persists for millions of years. The Kolmogorov spectrum turbulence that Voyager 1 detects in the interstellar hum, density variations following a specific mathematical pattern across astronomical unit scales, is consistent with turbulence driven by ancient energetic events and sustained by the ongoing dynamics of the interstellar medium. Voyager is measuring the weather, and the weather was set in motion by explosions that predate human civilization by a factor of 1,000. This is not abstract cosmology. The local bubble affects us directly. The density of the interstellar medium outside the heliosphere determines how much pressure pushes inward on the boundary. If our solar system were in a denser region of the galaxy, the heliosphere would be smaller. The termination shock would be closer. More galactic cosmic radiation would reach the inner planets. The heliosphere's size is partly determined by our star's output and partly by the environment outside. That environment is shaped by supernovae. Some researchers have speculated that past passages through denser interstellar regions may have temporarily shrunk the heliosphere enough to change the cosmic ray flux at Earth, potentially affecting atmospheric chemistry and climate over geological timescales. This remains speculative, but it is not unreasonable. We know the heliosphere changes size. We know it responds to external pressure, and we know the interstellar medium is not uniform. What Voyager detected at the edge of the solar system is not just the edge of the solar system. It is the boundary between our star's influence and the accumulated aftermath of every violent event in our galactic neighborhood for the past 20 million years. There is something that does not add up about the two heliopause crossings, and it goes beyond the differences in plasma readings and boundary thickness. Voyager 1 crossed at 121.6 astronomical units in August of 2012. Voyager 2 crossed at roughly 119 astronomical units in November of 2018, 6 years apart. Different directions through the heliosphere, different phases of the solar cycle. Voyager 1 crossed during a period approaching solar maximum. Voyager 2 crossed closer to solar minimum when the solar wind is weaker and the heliosphere should be smaller. A weaker solar wind means less outward pressure, which means the boundary should contract inward. Voyager 2 should have crossed the heliopause significantly closer than Voyager 1. It did cross closer, but only by about 2.5 astronomical units, roughly 230 million miles. Given the difference in solar wind conditions and the different trajectories through the heliosphere, models predicted a much larger gap. The similarity in crossing distance was almost as surprising as the differences in what each probe measured at the boundary. For decades, the heliosphere's size was treated as primarily a function of solar output. Stronger solar wind pushes the boundary out. Weaker wind lets it fall in. The 11-year solar cycle should pump the heliopause in and out by 10 astronomical units or more. This model is not wrong, exactly. The heliosphere does respond to solar wind changes, but Voyager's data showed that the external environment matters just as much. The interstellar medium is not a passive background. It pushes back. The local interstellar magnetic field, measured at more than 3 nanoteslas, exerts continuous pressure on the heliosphere from outside. The thermal pressure of the hot interstellar plasma adds to it. The ram pressure of the interstellar medium flowing past the heliosphere contributes further. The boundary is not set by our star alone. It is a negotiation. Think of it like a soap bubble floating in a breeze. The air pressure inside the bubble determines its tendency to expand, but the wind outside determines its actual shape and position. If the wind is steady, the bubble holds roughly the same size regardless of small changes in internal pressure. The interstellar medium around our solar system is that wind, and it is not weak. This changes how we think about the heliosphere's stability. If external interstellar pressure is as important as internal solar wind pressure, then the heliosphere's size and shape depend on galactic conditions as much as solar conditions. Our solar system is moving through the galaxy at roughly 52,000 miles per hour. The local interstellar cloud it currently traverses is not uniform. Density varies. Magnetic field strength varies. As the solar system moves into regions of different interstellar properties, the heliosphere will respond. It could shrink. It could change shape. It could, in principle, be compressed enough to expose the inner planets to significantly higher levels of galactic cosmic radiation. None of this is imminent. The current interstellar environment appears relatively stable on human timescales, but on astronomical timescales, the heliosphere is not a fixed shield. It is a temporary arrangement between a star and the galaxy it travels through. Voyager revealed that the galaxy's vote in this arrangement is louder than anyone expected. 2 probes, 2 paths, through a structure that extends in every direction. This is the fundamental limitation of everything Voyager has told us about the heliosphere, and it is a limitation worth stating plainly. Voyager 1 flew roughly in the direction the heliosphere faces as it moves through the interstellar medium, the so-called nose. Voyager 2 traveled at a different angle, roughly toward the southern hemisphere of the heliosphere. Neither probe sampled the flanks, neither sampled the poles, neither went anywhere near the region where the tail was supposed to be. Every claim about the heliosphere's 3-dimensional structure based on Voyager data is an extrapolation from 2 lines through a volume that spans hundreds of astronomical units in every direction. The Interstellar Mapping and Acceleration Probe will provide a 2-dimensional sky map of the heliosphere, collapsing the 3-dimensional structure into a projection much like a flat map of the Earth. This is a massive improvement over 2 trajectories, but a 2-dimensional projection still cannot unambiguously reconstruct 3-dimensional structure. To get the true shape, you need either many different vantage points or measurements that encode depth information. The probe's time series data, watching how the heliosphere changes over a full solar cycle, may partially substitute for multiple vantage points. As the heliosphere breathes, different regions move in and out, and the resulting changes in energetic neutral atom flux can reveal something about the 3rd dimension. It is an indirect method, and it has limits. The most direct way to answer the open questions would be to send a spacecraft to 1,000 astronomical units, far enough to look back and see the entire heliosphere in context. This is the interstellar probe concept that has been studied by NASA and Johns Hopkins Applied Physics Laboratory for years. It would carry modern instruments along a trajectory designed to complement Voyager's paths, sampling the flanks or the tail, the regions where anomalous cosmic rays might actually be accelerated, where the heliosphere's shape is most uncertain. The concept remains unfunded. No mission is in development. No launch date has been proposed. At current propulsion technology, reaching 1,000 astronomical units would take decades. The fastest outbound spacecraft ever launched, New Horizons, travels at roughly 36,000 miles per hour relative to our star. At that speed, 1,000 astronomical units is more than 40 years away. Voyager 1, traveling at roughly 38,000 miles per hour, will reach 200 astronomical units sometime in the late 2030s. That is still less than 1/5 of the distance to the proposed interstellar probe target. In the meantime, we have what we have. 2 aging probes, measuring local conditions along 2 paths. 1 new probe, measuring global emissions from near Earth. And decades of data that contradict nearly every prediction made before the measurements existed. The heliosphere is the only astrophysical structure we live inside and can study from both the inside and the boundary simultaneously. No other star system gives us that opportunity. But the opportunity is narrow. It depends on instruments that are losing power and a mission that has not been funded. We are drawing a continent from 2 footprints and a satellite photo taken from 1 million miles away. The continent is real, the footprints are real, but the map between them is still mostly blank. The power budget on Voyager 1 shows roughly 227 watts available from the radioisotope thermoelectric generators as of early 2026. Voyager 2 is similar. The plutonium-238 inside each generator decays at a fixed rate, and nothing can change that. 4 watts less every year. 4 watts is not much. A typical nightlight uses about 4 watts. But on a spacecraft where every instrument, every heater, every computer cycle runs on a total power supply smaller than a standard light bulb, 4 watts per year is a countdown. The cosmic ray subsystem on Voyager 1 was powered off in February 2025. Edward Stone's instrument, the one that discovered the anomalous cosmic ray problem at the termination shock in 2004, went silent. On Voyager 2, the low-energy charged particles instrument, built under Tom Crimigis, was shut down in March 2025. Crimigis is the only scientist in history to have built instruments that flew to all 8 planets. His detector on Voyager 2 no longer sends data. The plasma science instrument on Voyager 2, the one John Richardson's team at MIT used to make the only direct plasma measurement at the heliopause, was already powered down in September 2024. Every one of these shutdowns is permanent. There is no restarting an instrument once the power has been reallocated. The decision of which instrument to turn off is made by Suzanne Dodd's team at the Jet Propulsion Laboratory, and it is made based on which remaining instruments can produce the most scientifically valuable data per watt consumed. By the end of 2026, each probe will likely have 2 or 3 instruments left. The magnetometer and plasma wave subsystem are expected to be the last operating instruments on both spacecraft. They draw the least power, and they provide the data most relevant to the open questions, magnetic field measurements, and plasma density through wave detection. If the power decline continues at its current rate, these instruments may survive into the early 2030s. After that, there will not be enough power to run any science instrument at all. The spacecraft may continue to transmit a carrier signal for a few more years, a radio tone confirming they exist, but carrying no data. Then, even that will stop. No other spacecraft is heading toward the heliosphere's boundary. New Horizons, which flew past Pluto in 2015, is on a trajectory that will take it into the outer solar system, but it is not expected to reach the heliopause before its own power supply dies. There is no funded successor mission that will cross the termination shock, traverse the heliosheath, or sample the heliopause. When Voyager goes silent, direct measurement of the heliosphere's boundary ends. The interstellar mapping and acceleration probe will continue observing from near Earth, but 1.5 million kilometers is not 15 billion miles. Remote sensing and in situ measurement answer different questions. We are in the final years of a capability that took 50 years to achieve and that we have no plan to replace. Every month that the magnetometer and plasma wave subsystem continue to operate, they record measurements from a region of space that no other instrument can reach. That data may be the last of its kind for decades, possibly longer. The central question was specific. Why does nothing at the edge of our solar system match what we predicted? The termination shock was 14 astronomical units closer than models said. The anomalous cosmic rays did not peak where they were supposed to. The heliosheath was not smooth, but filled with magnetic bubbles the size of the distance between Earth and our star. The heliopause was 20% closer than predicted, and when Voyager 1 crossed it, the magnetic field barely changed direction, leaving scientists unable to confirm the crossing for over a year. The interstellar medium turned out to be 30,000 to 50,000 Kelvin, nearly double the predicted temperature, yet so diffuse that a human body would freeze in it. The heliosphere has no tail, its shape is unknown, its boundary leaks, and a persistent hum vibrates through what was supposed to be silent, empty space. 2 spacecraft crossed the same boundary and described it differently. The magnetic fields on both sides of the heliopause are aligned for reasons nobody can explain. An unknown pressure source pushes on the heliosphere from outside. Plasma density along Voyager 1's path has been 30% above normal for 5 years, with no identified cause. The source of anomalous cosmic ray acceleration, predicted at the termination shock, remains missing after 22 years of searching. The question is not answered, it has expanded. What started as an investigation into the edge of the solar system became an investigation into the relationship between our star and the galaxy. The heliosphere is not a fixed shield erected by the solar wind. It is a negotiated boundary, shaped equally by internal pressure and external force, breathing with the solar cycle, responding to interstellar conditions that change as the solar system moves through the galaxy at 52,000 miles per hour. The local interstellar cloud, the local bubble, the magnetic field structures left by supernovae that exploded 10 million years ago. All of these press inward and shape the bubble we live in. Right now, Voyager 1 is roughly 165 astronomical units from Earth, transmitting data at the speed of light that takes more than 22 hours to arrive. Voyager 2 is about 140 astronomical units out, on a different heading, measuring a different slice of interstellar space. The magnetometers on both probes are still recording. The plasma wave subsystems are still listening. The interstellar hum continues. The interstellar mapping and acceleration probe has begun scanning the entire sky from its position near Earth, building the global maps that will either validate or demolish the models that remain. Its first full results will arrive within the year. When they do, they will describe a heliosphere that two probes spent 50 years crossing, and that we still cannot draw accurately on a whiteboard. The investigation is not winding down, it is accelerating. The instruments are failing, but the questions are multiplying faster than the power is fading. Every year of new data from both the probes and the mapping mission will sharpen the contradictions or begin to resolve them. Either outcome changes what we think we know about the space between stars. And somewhere past 165 astronomical units, in plasma heated by dead stars, carried on a signal that takes almost a full day to reach Earth, the hum goes on,